Everybody. Today we're going to start chapter 4. So this is 4.1, kind of an introduction to the major topic for that chapter, which is rational functions. We use the term rational all the time in ordinary speech to mean, somebody who's logical, I suppose, who thinks clearly. In this case, it's really more a straightforward interpretation of the word. Rational here means something that's a ratio. So it's not really a very hard concept. Here's the definition, 4.1. A rational function is a function which is the ratio of polynomials. And we just spent a lot of time talking about polynomials. If you make something that's a fraction with a polynomial in the numerator and in the denominator, you get one of these rational functions. We can analyze rational functions really pretty nicely by thinking about the polynomials that make them up. For instance, let's think about what happens when you have a polynomial over a polynomial and the numerator is 0. Suppose you had, for instance, a rational function p of x that looked like, say, x minus 1 over, I don't know, anything crazy at all downstairs. Well, I can tell you where that's going to be 0 right away without having to think very much. You see, a fraction is 0 exactly when the numerator is 0. So p of x is 0 in one exact place. It's when in the numerator that expression is 0, which would be x equal 1. So let's take a look at a plot of that. I'm going to want to do a Desmos graph here. If I just type x minus 1 and then hit the divide sign, you see what Desmos does for me? It says x minus and then 1 divided by something. That's not quite what I want to do. So what I'm going to need to do to get a rational function like this is put parens around the numerator, then hit my divide sign. I don't have to use parens in the denominator. That's just the way Desmos works, because you see how I'm underneath of the long fraction bar? Okay, so I could put in this x to the second plus 5 times x minus 3. Wow, that's a strange looking graph. But the one feature I wanted us to look at was, where is it 0? 0 right there at 1. You see that it's just slightly above 0 out here. Yep. It comes down, has a low spot on this bit here, but never 0 in there. It's got this weird thing where it goes up on one side and down on the other, somewhere around minus 5. And then, it's getting close to 0, but does it look like it'll ever reach? The behavior we're seeing right there, where the value of the function is approaching something, that's a real common feature, especially of rational functions, but for functions in general. It's called an asymptote. Generally speaking, this is something which you approach, but you never quite equal. It can be lots of different things, and usually I'm thinking about a value, but it can also be, other curves. Let's for now just say a value that you approach, but never become equal to. Sorry, it takes a lot longer to write that than it does to say it. That's an asymptote. Value, or another type of thing that your graph will get closer and closer to, but never actually arrive at. So what we're looking at here is, values on this graph. As I move out here into negative territory, they're getting closer and closer to zero, it looks like, but they're never quite arriving. That means zero is an asymptote. Well, I think I need to do a better imagined or a better conceived example in order for us to see what asymptotes are about. But yeah, let's do that. So the great majority of the way we'll think about stuff in terms of rational functions depends on knowing what the factorizations of the pieces are. Now, apparently x squared plus 5x minus 3 has zeros, but I don't know what they are. So I'm going to put a form for something that will also start with x squared here, but which I know where the zeros are. So how about x plus 1? That'll have a 0 at minus 1. And x minus 2. So now when we could FOIL roll that out, it's x squared minus x minus 2. Yeah. But you can see where the zeros would be from the algebraic form. Well, not quite. Let me say this more carefully. The numerator is 0 at 1. The denominator is 0 at minus 1 and at 2. But that is not going to be a 0 of the function, because what actually is that? What is that going to be? It's a place where we're dividing by 0 on this graph. So if we back out a little bit from here, this has similar behavior to the one we looked at before. It has a 0 right there at x equal 1, but it has, I don't know. Well, these are called asymptotes too. Might as well draw them for you. They are vertical lines of the form x is equal to minus 1 and x is equal to 2. Sorry, I want to make these be the same color. And also, typically we draw asymptotes as dashed. Right. So that, in fact, there's one more thing I'd like to do in terms of setup here, which is to make the what? Oh, wow, that's weird. I'm not seeing maybe they've updated things, but usually there's a projector mode thing under that. I don't have it anymore. Huh. So you can, what do you do to make the things bolder? I guess we don't. New update to Desmos. Anyway, you can see these places at 2 and at minus 1 where the expression for this rational function would have division by 0. And that means at those points we're undefined, right? You can't actually evaluate at -1 or at 2. And if you look at this graph, you look at this picture, you realize, yeah, that's right. There is no graph directly above -1. This dashed line is there, and the graph is approaching the dashed line, but it's never arriving at it. So, yeah, we've got a hole in the domain of the function. This particular graph, well, let's see, we're talking about it, but let me go ahead and copy the formula down. It's x minus 1 over, I'll think about expanding that out. Let's see, x squared minus x minus 2. So if that's a function f of x, what we've found, well, we had previously said if it's got x minus 1 in the top, it'll be 0 at 1. But this is undefined whenever the bottom is 0. So this guy is undefined at x equal minus 1 and 2. And that means the domain of the function we're talking about there, domain of f, is one of these intervals. It's a little bit hard to write. It goes from minus infinity up till you get to minus 1, not including minus 1. Then it goes from union minus 1 up to 2, again, not including those, and then from 2 to plus infinity. That's the domain. While we're on it, what do you think the range of this function is? Well, you can tell the range from just this part in the middle. You see how we've got a value of 0 right there at x equal 1, and as we head in this direction, we are going higher and higher and higher. If we head towards the other blue dashed line, we're going lower and lower and lower. Does it make sense that we're approaching plus infinity on one side, minus infinity on the other? That's enough to find one place where the range shows that you've got all real numbers in order to know that that in fact is the range. All right, so that seems like a pretty easy analysis, I think. You look at a rational function, you factor the top and you factor the bottom, and you find out where the tops are 0. That's your zeros. You figure out where the bottoms are 0. That's these weird things, the so-called vertical asymptotes. Well, it doesn't quite always work that way. So let me give you another example. If we put x squared minus 1 there, and yeah, well, that'll do. Well, I've lost something. I apparently don't need this vertical asymptote line at x is equal to minus 1, so we'll just turn it off. Well, that's really a lot simpler. It's weird because I made the graph more complicated, and I made the equation more complicated. I put a square where previously was just an x, but the graph became simpler, or it seems to have become simpler. It's actually more complicated in a sneaky way. Let's go ahead and copy that formula down. I had x squared minus 1 over x plus 1 times x minus 2. That's our function. Okay. The numerator is not factored, and notice it's a difference of squares, so it's easy enough to factor it. You get x plus 1 times x minus 1 upstairs. And then, of course, we have x plus 1 and x minus 2 in the bottom. So look at the top and figure out where it's 0. The numerator is 0 at 1 and also at minus 1. But look at the graph. At 1, oh, that's 2. At 1, oh, good, it's 0. But at minus 1, it seems to be, well, somewhere around 0.6. No, oh, weird. I landed right on minus 1, and now the graph is saying the y-coordinate is undefined right there. You see that popping up? What's happened? Well, it's this. There's an x plus 1 factor in the bottom and an x plus 1 factor in the top. I would love to just say cancel them, right? But if I cancel them, the new function I create would be defined at negative 1. It would have a value at negative 1, whereas this guy does not have a value at negative 1. So there's sort of, I don't know, there's two functions. They're very, very close to one another. This function, let's go to f of x, the one we've started with, x plus 1 times x minus 1 all over x plus 1 times x minus 2. That guy's domain, well, what is it? The only thing it can't have is x equals to 2. It would appear, but that's not quite right. Like I just did it. When I traced it, I saw that when I tried to move a point along it, I saw that when I'm right at minus 1, it's undefined. And you can see that algebraically too. This formula, when you put in -1, you get 0 over 0. So the domain of this thing is from -infinity up to -1, union with 1 to 2, union with 2 to infinity. There's a related function, closely related function, let's call it g of x, which is what you get if you do the cancellation of the x plus 1 over the x plus 1. It's just x minus 1 over, oh, actually I don't need the parenthesis, x minus 2. What's the domain of that? Very similar. There's just one extra point that your function will be defined at, whereas the thing above was not. So this guy is going to go from -infinity all the way to 2, and then from 2 to infinity. So whereas the plot above was missing x equals -1, this one has a value at x equals -1. So you might not completely believe me, but let's go ahead and plot that graph. It's just x minus 1 divided by x minus 2. Landed right on top of the thing I was graphing before. So it has the same vertical asymptote, but this graph, when you get to, oh, if I can just get it to, I can't see, oh, there it is, right on -1, it's got a value. So there's not a huge difference between these two things, but there is a difference. It's a little bit subtle. The way we say this is that f of x has a hole at x equals 1, -1. And I meant to say g there. G of x has no holes. Okay, so there are three features that you can see from the factorization of well, both parts of a rational function. The what we call the local picture. And now we know what they are. We've seen all three of them. Local features. Zeros is the easy thing to see, that's where the numerator is 0. There are vertical asymptotes, which we're always going to write as VAs. And finally, there are holes. And these three items, we can tell right away from the factored form of, well, yeah, again, factoring both numerator and denominator, you'll be able to see those local features. I like to think of it as there's the graphing window that we're looking at, and these are the things you're going to locate in the window. There's also a sort of a big picture, or what is often called the global behavior. So we'll have local features that you see kind of in the graphing window, and then global behavior. What is that? Well, we already talked about some global behavior when we dealt with polynomials. There was like goes up on both sides, or it goes down on both sides. There's up on one side, down. There's all those possibilities. Rational functions have those same possibilities, but then some additional stuff. For instance, the particular rational function we're looking at right now, as you go to larger and larger values, what do you think the y-coordinate is approaching when we get out here to big numbers? Well, let me point out what the formula says here, and then ask you to think about it for x being really gigantic. So, sorry if I can make that bigger. Okay. If I have x minus 1 over x minus 2, and x is like 1,000,000, right? 1,000,000 minus 1 over 1,000,000 minus 2. I don't know, those numbers are both, if we're rounding, they're both 1,000,000. It's basically the top and the bottom are equal. Yeah. I mean, they're not quite equal, but it's so close. 1 part in 1,000,000 off. So the fraction ends up approaching 1, and that's what you're seeing right here. There's a tendency for the numbers to get closer and closer to 1. Same thing on the back zone. I'm not going to be able to see as much of it, but see how the values are getting closer and closer to 1. These guys are approaching 1 from underneath. They're 0.96, then 0.97. They're growing towards 1. On this side, they're descending towards 1. We're starting out with values, but whatever, everybody's heading towards 1. If I were to plot y equals 1 on here, let's get the with a dashed line on it. I feel like maybe I want the color to keep the color as blue for this guy. I can't seem to turn it back on. Oh, there it goes. Yeah, I'm going to make the color be blue again. So that's an example of a global behavior. As we go to large values outside the usual graphing window, we're approaching something. In this case, it's approaching 1. So that is known as a horizontal asymptote. We can have other kinds of asymptotic behavior as you go off towards large values. But one case we ought to single out and mention is you often have a horizontal asymptote that is 0. So you can have a 0 asymptote. That is, instead of some particular value you're approaching, you're just getting closer and closer to 0. A 0 asymptote. When would a rational function have a 0 asymptote? Well, I should probably show you some examples. Let's just knock out all of these things. Suppose I had something in the numerator that was a relatively small polynomial, and then something in the denominator that wasn't small. So what I've got here is, let's go ahead and give a expanded form of that. It was a x to the second minus x minus 2, wasn't it? What am I doing looking at it way out here? Let me go back to the middle. Okay, so when you're in the middle, when you're in the usual window, you're seeing all these features, a 0 and a vertical asymptote and another vertical asymptote. But if I ask you what's going to happen in the long run as x gets to very large values, look at what you'll have. In the numerator, and I always jump to 1,000,000. If we put 1,000,000 in for x, what are we going to have in the numerator? Basically 1,000,000. 1 less than 1,000,000, you'd round it to 1,000,000. But in the denominator, what are we going to have? Well, it's got 1,000,000 squared in it, which is a trillion, minus 1,000,000. This is funny. I mean, I usually think of 1,000,000 as being a big number. But when I've got 1 trillion minus 1,000,000, geez, it's like the federal budget right now. They're spending almost $2 trillion on coronavirus relief. $1 million in ordinary life seems like a big quantity, but changing that bill by $1 million, it hardly matters, right? So x squared minus x, when x is 1,000,000, is basically still x squared. It's 1 trillion. So what are we looking at if we have 1,000,000 divided by a trillion? Might as well be 0. It's like 1 over 1,000,000. Yeah. All right. So when do you get 0 asymptotes? I'll tell you when. This happens when the degree of the numerator is smaller than the degree of the denominator. Anytime you have the degree of the numerator less than the degree of the denominator, you're going to have a 0 asymptote. When do you think you get a horizontal asymptote? Well, that's when the degrees are equal. And now that you know that, you can create pretty much any horizontal asymptote you want. You just make the leading coefficient of the two polynomials, have that ratio. Give you an example. Suppose I wanted to make 5 here, that level right there, as our horizontal asymptote. I can do that by creating another polynomial that has a 5 up front and the same degree as what's in the bottom, and I don't care what else. There. Well, that was weird. Changed a lot from, let's just leave it like that. 5 times x squared plus 3x over x squared minus x minus 2. Crazy looking graph, but I was just asking about what, creating asymptotic behavior. Do you see that it's approaching the line where y is equal to 5? Sure is. That's the asymptote. That's the horizontal asymptote for that graph. All right. I said we could have other behaviors, and now you're in a good position to see how that would happen. When the degree of the numerator is smaller than the degree of the denominator, you get 0 as an asymptote. When they're equal, you'll get a horizontal asymptote, and by adjusting the coefficients, you can make that be whatever you want. Or probably the reverse way of looking at this is, given two polynomials whose ratio is a rational function, just compare the leading terms, and you will be able to tell what the horizontal asymptote is. If you're expecting to get something besides this, you have to look at the third alternative, and it would be if the degree of the numerator is larger. Yeah. This is called a slant asymptote. Well, the first case of it I'm going to deal with is called a slant asymptote. And that happens when the degree of the numerator is bigger than the degree of the denominator by 1. It's 1 bigger than the degree of the denominator. Right. Let's make one. I'm going to have something, well, if I'm going to keep x squared minus x minus 2 in the bottom, this is going to have to be x cubed. I don't want that 5 in there because we don't want to blow it up too much. Actually, that's a pretty decent looking one. What is the asymptote here? What is the thing? I said it was called a slant asymptote. Maybe you see it. We don't need that. What particular line is this thing approaching? Well, the answer to that is what we were doing last time when we did long division. So let's do a quick long division here. The numerator of that polynomial, or that rational expression, is x cubed, nothing in the x squared, and then 3x here, and then nothing in the constant term. The denominator is x squared minus x minus 2. Remember that we can't do synthetic division in this scenario because I've got a nonlinear thing as if the degree of that the divisor is larger than 1, you can't use synthetic. But let's see, x squared goes into x cubed x times. Stick it in that column. Multiply back and you will get x cubed minus x squared minus 2x. Subtract all of that from what's above. You're going to get, x cubed minus x cubed is gone. Nothing minus x squared, so that's x squared. 3x minus negative 2x. I think we're getting 5x right there. Yeah, and how many times does this go into that? X squared goes into x squared once. Multiplying back, we get x squared, of course, minus x minus 2. We'll subtract that from what's above, and that leaves us with 6x plus 2. Now, oh, I'm off the screen, sorry. 6x plus 2 is a remainder. And that means, well, let's say what this means for us. If you look at the original rational expression I had, x cubed plus 3x divided by x squared minus x minus 2, you can re-express that as just x plus 1 plus the remainder we just got, 6x plus 2, divided by the divisor. This piece right here, that's your slant asymptote. And this other piece is something that, as they say, goes to 0. It's not equal to 0, but the degree of the top is smaller than the degree of the bottom. So when x is large, it's going to be closer and closer to 0. All right, so that tells me that the graph or the curve I want to plot for the asymptote here is x plus 1. Let's, sorry. I see you have to have it on when you hit the gear. And then I'm having a hard time navigating for some reason. What do I need to do to change the style of the line again? I don't know. Okay. I think I'm just messing up that. There we go. There's the style. So dashed line. Sure, leave it blue. That's fine. I'm just wondering if I can change that to make it thicker. No, that's not what does it. Anyway, we don't need to know that. So given the polynomials that I've got here forming a rational function, you do long division to figure out what the slant asymptote would be. And then you do things like, well, when is the numerator 0? I can tell you where it's 0. It happens at 0 for sure. And it also happens when x squared plus 3 is equal to 0. There's no such place. So the numerator here has a single 0 when x is 0. And that's what we're seeing out of the function. It crosses through 0 only when x is 0. Do we have some vertical asymptotes? You got to refactor that thing again. But yeah, when x was minus 1, that was a vertical asymptote. And when x was 2, that's a vertical asymptote. I guess I ought to really get in here and adjust these styles again. Blue. There we go. So now you can sort of see all the bits of this. Two vertical lines that the graph approaches, a 0 right there at 0, and a slant asymptote. So pretty unusual looking graph. I can't really imagine too many situations where I'd want to have a graph that looked like this. But one of the values, or one of the advantages of rational functions is they can do things that polynomials can't. For instance, no polynomial function can approach a straight line like this. They always take off towards infinity, curving up or curving down. This guy's straightening up as we head out. So yeah, I can imagine situations where I'd like to model some phenomenon with a thing that eventually goes out towards a straight line. All right, so that's a whirlwind tour, introduction to rational functions. We're going to be spending a bit more time on them, but not too much, to be honest. I want you to know some basics about them, and then we're going to be pushing on to logarithmic and exponential functions. All right, that's it for today.